I'd like to focus on a question that students ask about what's the difference between r square and small r square. Okay, are they always the same thing? Are they different? And I'd like to try and illustrate this by using this in lecture exercise 6. Okay, so if I go to that in lecture exercise 6, really what this question asks you, it says define the sample correlation coefficient as R. So R is sample correlation coefficient. And that's what that is. And in this problem, it looks like in the simple linear regression model, so when we are in this simple linear regression model where we have y is equal to beta 0 plus beta 1 x plus epsilon, when you have this simple linear regression model, it turns out that this small r square is equal to the big R square. So you might wonder, oh, but what is this, right? So sample correlation coefficient, think of this as the correlation, sample correlation between x and y. Okay. So you could say, oh, the R square is measuring nothing more but the sample correlation between x and y, all of that squared. So it's always positive, right? So if the sample correlation is -1, the R square would be 1. The sample correlation is 0.5, the R square would be 0.25, etc. Okay. So in this particular setting, they're the same. They measure the same thing. Now, in a previous video, I tried to kind of prove this. Jordi will be providing some of the solutions of this, but let's go over this solution of this particular one where we show that in the simple linear regression model, the R square is indeed equal to the little r squared. Okay? Start with the definition of R square. Use the fact that you know exactly this is a simple linear regression, so I can substitute the beta 0 hat. I can substitute the yi hat with the below. Use the mechanical property here. This mechanical property will allow you to write this for y bar. So the beta 0 and beta 0 will simplify. You'll be left with just beta 1 hat. Right? All of that squared, so if you pull it out of the notation, it will be beta 1 square hat. Okay? That would be your R square at that stage. Now here's one thing that we did not do in the video, and perhaps in the previous video, and perhaps I should have kind of hinted towards this, is that at this stage you could have gotten stuck. Okay? You could have gotten stuck on what to do here. But we know the formula for beta 1 hat, and this is the formula for beta 1 hat from your lectures. We've derived this in question 6 of the problem set 2.1. And after we do some of the simplifications here, then these two expressions turn out to be exactly the same. Okay? So in the simple linear regression, R square and little r are exactly the same thing. Okay? What about if I have multiple regressions? What if I don't have a single x, but I have many x's? Now the little r and the big R cannot be the same anymore. Okay? So what is then, this is only in the simple linear regression. Simple linear regression. What about if I have multiple linear regression? Then how does this sample correlation and R square relate with the two? Well, here's how they relate with the two. Sample correlation of y hat, the fitted value, and y will be equal to R, such that R square is equal to this. So now you're doing the correlation coefficient between the fitted values and the y. Okay? That's what you're really doing over there. You could have thought about this being the same thing. Sample correlation of x and y will be the same as the sample correlation of y hat y. And that might be a very good homework to try. Can you show that the sample correlation in the simple linear regression model between x and y is the same thing as the sample correlation between y and y hat? So let's summarize. Sample correlation, or the little r, in the simple linear regression model is exactly the same as the r square. The moment you move away from a simple linear regression model where you have more than one explanatory variable or non-constant explanatory variable, that stops being true. And the problem that we just did, so problem 7 of 2.1 that we did in this previous lecture, really showed that, right? You didn't need to, at any point, I didn't need to assume that I was dealing with a simple linear regression model. Right? At no stage did I assume that I was dealing with just one explanatory variable or non-constant explanatory variable. And that's really the relationship between these two. So stop here.